Hello, class. So today we are talking about the momentum and impulse problems. Now, I told you I'd promise that I would post an answer key for this, and so that's what I'm going to give you guys right now. That way you guys can do a little check for yourself to make sure that you are getting this. All right, so for number one, we are looking at a 50-gram cart. Cart number one is pulled with a 1 Newton force for 1 second. So cart number one is, oh sorry, 0.5 kilograms. It is pulled with a force of 1 Newton and it is pulled for 1 second. Cart two, that's one. Cart number two has a mass of 0.5 kilograms. It is pulled with a 2 Newton force and it is pulled for half a second. So, looking at this, we have to keep all of this in mind. So let's look at our first one. Try and focus a little more for you guys. There we go. Let's look at our first one. Which cart, number one or two, has the greatest acceleration? So which one has the greatest acceleration? Well, think about this. Acceleration depends on force. So because they both have the same mass, Newton's second law says sum of the forces equal ma. Acceleration depends on force. If you make the force bigger, the acceleration has to be bigger, which means the one with the bigger force has the greater acceleration. So bigger force yields bigger acceleration. So that tells us that number two is our answer for that one, cart number two. Let's take a look at B now. Still for number one, which cart, one or two, has the greatest impulse? So now we're looking for the greatest impulse. So I want you to remember this now. Impulse is force times time, right? Impulse. Oh, actually, I don't know if we ever talked about this. J is impulse equals Ft, right? Impulse equals J, which equals Ft. So we can just simply calculate this. So for cart number one, it is equal to 1 times 1, which is 1 Newton second. And for cart number two, it is equal to 2 times 0.5, which happens to also be 1 Newton second. So we find out that the impulse is the same for both carts 1 and 2. And then last, we'll talk about the third part of the equation. Which one has the greatest momentum change? Greatest delta P, greatest momentum change. And we know that impulse, by definition, equals delta P equals a change in momentum. So if we just realized that the greatest impulse was the same, that means the delta P is the same for both as well. They both have the same change in momentum. What these problems were doing, they were just simply changing the words around and having you look at these problems from different angles, but kind of asking the same questions. All right, let's move on. It's now number 4 on your sheet. The diagram to the right depicts a car before and after the collision. So let's take a look at that diagram. So we have this diagram right here. Diagram to the right depicts the cars before and after the collision. We're just going to leave it right there off to the side. The speeds of the cars are given. In case A, the car bounces off the wall. In case B, the car crumbles and sticks to the wall. Answer each question. So, let's take a look. Let's move this over right there. So, For part A, in which case A or B is the change in velocity the greatest. Think about a number line. So for case A, we go from 5 plus 5 meters per second to minus 4 meters per second because we're changing direction. We have to go plus 5 all the way down to 0 where the car stops and then reverses and goes minus 4. So this is an overall change, of 9. Whereas in case B, the car goes from plus 5 meters per second to 0, which is just a change of 5. So case A is your greater change in velocity. For B, let me make this any clearer. For B, let's take a look. In which case A or B is the change in momentum the greatest? Well, remember, change in momentum equals m delta v, where delta v is the v final minus the v initial. So essentially, this is just asking, change in momentum is based on m delta v. Delta v is based on your change in velocity. Which one has the greatest velocity? Right there. So case A is also the answer for the second one. Again, it's asking the same question, just different ways. Let's take a look at part C. And they're all related, right? All these questions are related to one another. In which case A or B is the impulse the greatest? So now we know that impulse equals, by definition, is change in momentum, which is also F times T. Well, we just said in part B that the one with the greatest change in momentum was case A. Well, guess what? Impulse is change in momentum. So which one has the greatest change in momentum? Case A. Which one has the greatest impulse? It's case A again. All right, just different ways of asking the same question, guys. That's all it is. All right, for part D, in which case A or B is the force which acts upon the car the greatest. Assume the contact times are the same for both cases. So now we want to figure out which one is the force the greatest. Well, force appears in our impulse equation. Now, if we're assuming that the T's are the same for A and B, that means in order to get a bigger impulse, you have to get a bigger force. So that would mean, you guessed it, if case A has a bigger impulse, okay, we talked about that, it also has to have a bigger force as well, because they are directly proportional. You increase one, the other has to go up. Okay, there's no ifs, ands, or buts about it. All right, let's keep moving on. Let's move on to number 5. Jennifer, who has a mass of 50 kilograms. Mass is 50 kilograms. Get my handy dandy calculator here. So I know we got some maths coming up here. Some math. She's riding at 35 meters per second. Meters per second in her car, red sports car, when she must suddenly slam on the brakes to avoid hitting a deer crossing the street. Here's our little deer. You guys can laugh at this in the privacy of your own home. He's got his little antlers there, his little tail. So that is the little deer that we want to protect. We got to protect that deer. She strikes the airbag, which brings her body to a stop in a time of 0.5 seconds. All right, what average force does the seatbelt exert on her? We want to find the force. We know this is the initial velocity, and we know the final velocity she comes to a stop is 0 meters per second. So we want to solve impulse. Impulse equals Ft equals m delta v. Our force is what we're looking for. Our T is 0.5. Our mass is 50. And our change in velocity, well, that would be the final 0 minus the initial 35. F times 0.5 equals 50 times negative 35. F times 0.5 equals, let's multiply 50 times negative 35. That gives us negative 1750. Now what do we do? Correct, we need to divide. So in doing so, when we divide by 0.5, it's like multiplying by 0.2. So we get a force that's equal to negative 3500 newtons. Remember, the negative just implies the direction, okay? That is direction. It is opposite to that of movement. Now, second part of the question says, if Jennifer had not been wearing a seatbelt and she had not had an airbag and the windshield stopped her instead, what would the force have been? So all of this will be the same except for the time. The time now becomes 0.002 seconds. So I want you to think about this for just a second. Okay, guys? We talked about this with impulse. Impulse equals Ft. All right, she's going to have the same impulse. She's going from a velocity of 35 meters per second to a velocity of 0 meters per second. In both cases, she's still going to have that. But here's the difference. It's the time. So if the impulse number stays the same, and the time in the second case goes way down, what does the force have to do to keep this the same? Yes, you're correct. You got this. Thumbs up. The force has to go way up. So that means the force we get in the second problem should be a whole heck of a lot higher than the force we got in the first problem. And let's see. Ft equals m delta v. F times 0.002 equals 50. I'm just going to shortcut it a little bit because it's the same idea. Times negative 35. F times 0.002 equals negative 1750. We divide. Let's do this out and see what we get. F comes out to be 1750 divided by 0.002. Negative, opposite direction. That's all that negative implies is direction. 875,000 newtons. So you could see by lowering the time, we increase the force. And this is what we talked about, or I tried to explain to you guys about the egg drop. You want to increase that time so you decrease the force. This is why when boxers box, right, they wear boxing gloves, right? It absorbs the impact. If you just box with your fists, there's not a lot of absorption there. Okay, guys? All right. Two more questions to go. We have number 6. A hockey player applies an average force of 80 newtons to a 0.25 kilogram puck. We have the force, we have the mass. For a time of 0.1 seconds, we have a time. Determine the impulse. We want the impulse. Now, many of you have probably set up this equation, and you're not wrong. But just remember, this is equal to impulse. So the whole reason we could set these two equal to each other is because this side equals impulse, and this side equals impulse. So when it's asking for the impulse, you could use either F times T or M delta V. You've got an F, you've got a T, you've got an M, but you don't have a delta V, so don't even use this equation. Just use 80 times 0.1, and that will give you 8 Newton seconds. That is your impulse. And then last, but certainly not least, we have number 7. And what number 7 is looking at, a 5 kilogram object, so mass of 5 kg, experiences a 10 Newton force for a time of 0.1 seconds. What is the change in momentum? Guess what, guys? Change in momentum is impulse. And we just learned that impulse is really F of t or m times delta v. So just do the F of t again. 10 times 0.1, we get 1 Newton second. That is our impulse. That is also our change in momentum. All right, guys, I hope this has helped you to understand this worksheet a little bit. Make sure you get this worksheet done. Please use the honor system. Get it done ahead of time. Check your answers. Send it to me. That way we can mark you down and you'll be good to go. All right, guys, get working on that study guide because we have a test coming up pretty soon. And email me with any questions. All right, take care, guys. Bye.